All right, so let's talk about chapter 4, which is on marine sediments. In the ocean, basically what's on the bottom of the ocean floor is sediment, and sediment is just particles of organic or inorganic matter that settle to the bottom through the water column and will accumulate in loose, unconsolidated masses, I guess you could say. Essentially, you can think about it as if you were to have a jar and you had some water in it and you went to go sprinkle or maybe not a jar. Let's try a cup of coffee, and you wanted to put some cream and sugar in it. So when you sprinkle that sugar into the cup, that sugar is going to dissolve, but it's also the ones that make it down to the grains that make it down to the bottom of the cup. They're going to just settle very loosely and just wherever they fall at. That's the same thing that happens with sand and other particles in the ocean. From the sediment, you're going to get layers building upon layers, and essentially scientists have used these different layers to look at what's been going on in Earth's history in the past. We can see movement of tectonic plates. We can see past climate change. We can see different ocean patterns that happened before, and we can see cataclysmic events. So let's take a look at some of these. But first, let's talk about how we actually collect this sediment. So you can see here we have a drilling rig, and you can see that drill rig on top of the boat. Essentially, you can think of these ships as just floating drill rigs, and they have a rotary drill, which at the drill head has these 2 or 3 round gears that rotate, and they essentially just break up any material as they're drilling through the sediment. And this allows scientists to see what's been going on. So they break up that sediment, the drill bit goes down, breaks things up, and then they shove a sleeve, like a hollow core sleeve, and they shove it into the sediment and then pull it back up. And what they get is a very nice core, which you'll see here on this slide. You see this scientist here. He is picking out different things from this core that he has sliced in half. And you can see that there's different things going on in that core right there. But essentially, this field of study is known as paleoceanography. So this basically means that it's the study of the ocean, the atmosphere, and the land interactions that have produced changes in the ocean chemistry, circulation, biology, and climate. So that was a mouthful, wasn't it? So essentially you can see here that in oceanography, everything is related. Whatever happens in the atmosphere will make changes in the ocean. That'll make changes to the biology of the ocean, and so forth and so forth. And you can see all of those changes within the sediment. So what kinds of sediment do we have in the ocean? We have these 4 types right here: lithogenous or terragenous, whichever one you prefer, but they mean the same thing. Essentially, that means that this type of sediment was derived from land. Then we have biogenous, which is derived from organisms. Hydrogenous, which is derived from the water. So that just means that anything precipitated out of the water. So it went from dissolution to precipitation. And then we have cosmogenous, which is from outer space. So we'll touch a little bit of these in a little bit. But 2 types of movement for these sediments are authogenic and allogenic. So authogenic sediment stays where it was generated. So let's just say in biogenous, you had a bunch of plankton up at the surface, and they were doing their thing, photosynthesizing, and then they came to their life's end and they died. And then their shell or plates or whatever it was that was covering their bodies starts to sink. in the water column, and as it sinks, it just sinks straight down unless there's a major current. But generally speaking, it'll sink straight down from where it was generated at, and that would be autogenic. Allogenic is sediment that's transported by water or wind. So let's just say that those plankton, when they died in a really strong current, so their shell or plates are going to be transported by that current to a different place. Or let's just say if you had a large windstorm on land that pushed a lot of soil into the ocean, that would be allogenic, because you're moving that sediment from point A to point B. Whereas autogenic, you're just leaving that sediment at point A. All right, so on the next slide, you have table 4.1, which is, again, another classification for sediment in the ocean. This is straight out of your textbook, so I definitely recommend you go and take a look at it in your textbook. So the first one we're going to touch on is lithogenic or terrigenous sediment. So as you can see here, there's 4 different types of lithogenic sediment. The first one is continental runoff. So essentially, it's just your wind, or like if there's a huge storm on land, any of that soil that gets washed into the ocean, that would be continental runoff. So the image that I have here would be that big dust storm on the bottom left-hand corner. That would be continental runoff. Volcanic eruptions is the next type. So any of that dust or magma that, well, not magma, it should be lava, but any of that lava that ends up into the ocean, that would be considered lithogenic sediment. So in the top right-hand corner image there, you can see Mount St. Helens erupting. All of that ash eventually ended up either on land or in the ocean after falling out of the sky. But all that ash that didn't end up on land, eventually it would have made its way to the ocean because of rain. So that leads into the third point there, rivers. So because rain carries sediment into the ocean, rivers are used as the, let's just say, super speedway into the ocean, and any of that sediment that gets into the rivers will get into the ocean. So you can see the image right below Mount St. Helens. It's kind of in the middle to the right there. That's an image of a stream dumping out lots of sediment into the ocean. And lastly, we have glaciers. Glaciers move a lot of sediment as they're receding or pushing forward or receding. And the bottom right hand image there, you can see a glacier is melting. That's an image of a glacier melting. But as it melts, it's carrying all of that sediment that used to be under it down into the ocean. So there are your 4 different types of lithogenic sediment types that you can find in the ocean. Next, so how lithogenic sediment ends up in the ocean is essentially that bottom right hand image there. You can see that wall of rock, and as time passes, wind and the rain will create fissures within the rock, and excuse me, and over time those fissures will continue to get larger and larger until parts of that rock break off. So you can see that hiker there standing on a piece of rock that fell off of that wall. And eventually, if you continue going further and further in time, those rocks that fell off will continue to erode and become smaller and smaller, and eventually will make its way into a stream or a river where it will continue to erode and become smaller and smaller until it gets down to the beach. And then it'll become part of the beach, part of the sand of that beach, and then eventually it'll make its way into the ocean. All right. So generally, lithogenic sediment is comprised mainly of quartz, so silicon oxide. And this is mainly what a lot of the land material is made out of. So when you look at a close-up of soil and whatnot, that's derived from mountains. You will see a lot of quartz minerals. Typically, you will see coarser sediment when you get closer to the shore, but then as soon as you get out into the deep ocean further away, you'll see finer grained sediments, and that's purely because it's had more time to erode and break down. So it's a stepwise process. You'll see very large boulders up in the mountains. Once you get to the beach, you'll see smaller fragments of those rocks. And then by the time you get into the deep ocean, you'll see very fine-grained sediments. All right, so I was talking about grain size on that last slide, but this is really important because it'll tell you how much energy is going into transporting that sediment from either the mountains down to the beach or to the beach into the deep ocean. So if you have a lot of energy at the beach, you should expect finer grained sand, versus if you are at a calmer beach like Ala Moana Beach Park, you shouldn't expect to see, reverse that. If you have a lot of wave activity, you should expect larger grain sand, because the larger wave activity is not only breaking up those particles, but they're also carrying away the lighter grain, finer grain sand back into the ocean. So at a beach like Ala Moana, you should see finer grain sand, because that fine grain material is not being pushed out into the ocean, it's staying on the beach. So at the bottom here, you can see table 4.2 from your textbook. This just gives you a breakdown of the different size classifications that we use for sediment. And you can see we start all the way at the top with boulder size, which is greater than 256 millimeters. And then we get all the way down to fine grain, which is your clays. And they are really, really tiny. On this next slide here, again, just to recap, the different types of sediment origin are from weathering and erosion from land, activity from living organisms, accumulation of dead organisms, and we'll talk about those oozes later on, volcanic eruptions, chemical processes within the water itself, so precipitation, and space debris. So we'll talk a little bit about the rest of them in a sec. And again, you can see the different size classifications for the grain size. Now, in the ocean, you have two different ways in which sediment can be distributed. You can have neritic, or you can have pelagic. So neritic are regions near the coastline, so your continental shelf region, or your continental margin, I should say. And these are shallow water deposits. They are close to land and are predominantly lithogenic in nature. And they will deposit quickly because they tend to be larger grain, larger in size. Whereas pelagic, these tend to be in the deep ocean. They are finer grain sediments because they've had more time to break down and erode into smaller sediments, and they will deposit slowly because they're not as large, they don't weigh as heavy, so they will slowly take their time getting into the deep ocean. So neritic lithogenic sediments, you have these four right here. You have beach deposits, which are mainly quartz minerals, and they contribute to the sand. Well, it is the sand on the beach. And waves generally will break these down into smaller and smaller grain sizes. Then you have continental shelf deposits, which are relic sediments. So they are sediments that used to be on the beach, but now they're on the continental shelf. They're making their way into the ocean, and they're becoming, they should be becoming smaller grain sizes. Then you have turbidite deposits, and these are the layering that you see from turbidity currents in the submarine fans, and you'll see the layering in these deposits. And then you have glacial deposits. These are on continental shelves in the high latitudes in the polar regions where you have glaciers, and some of these are created because of ice rafting. So a lot of times you'll have glaciers that extend over the water, and parts of that glacier will break off during the summertime when it warms up, and you'll create these floating ice pieces known as, they're similar to icebergs, but they carry sediment with them out into the open ocean. Now, pelagic sediments tend to be finer grained because they've had more time to erode and break apart. They will slowly make their way through the water column down to the bottom of the ocean. And typically, pelagic lithogenic sediment tends to be comprised of volcanic ash from eruptions, wind-blown dust. So when you have those windstorms that blow a lot of material out into the ocean, that's what settles. And then any fine-grained material that's transported by ocean currents. So these are typically material that started off on the beach, made their way into the continental shelf, down into the deep ocean, and was carried through the deep ocean by the currents. So these pelagic deposits, you can see an image there from a submersible. They are known as abyssal clays because they are super fine grained. They tend to be very silty, very small in size, and typically 70% of the particles in this abyssal clay is from land. You tend to see a lot of iron in the abyssal clays, and that gives it the reddish color, which you can't see in this image, but if you were to bring the sediment up to the surface, you would be able to see that reddish color. And typically abyssal clays are the predominant sediments in the deep ocean if you don't have other type of sediments, which we will cover in a little bit. So next, so that was all lithogenic sediment, so it was a pretty wide category. But now let's talk about biogenic sediment. And biogenic is, as the name suggests, from biology. So it's created from either those plankton-like shells that you see in the bottom right-hand corner there, or in the top right corner there, the image shows you a parrotfish, which is very, very productive at creating sand in the coastal regions. So biogenic sediment can be made out of calcareous or siliceous material. So calcareous just means that the sediment is made out of calcium carbonate. So the same thing that your bones are made out of, the same thing that coral reefs are made out of. Siliceous just means that it's made from silica. So very similar to some in the image in the right-hand corner there, on the bottom right-hand corner, one of them says radiolarians. They make a shell that's made out of silica. These types of sediments are only abundant in areas where you have high biological productivity. So you have to have a lot of biology in order to create these types of sediments. And the only time you can have an ooze, which does not sound like, an ooze is not slimy, like you would think. An ooze just means it's a pelagic sediment that contains more than 30% volume of plankton shells or tests. All right, so it just means that when you look at this sediment under the microscope, what you see is a ton of shells instead of a ton of rocks like you would see at the beach. All right, so biogenic sediment generally is the remains of living organisms. So you see that paramecium over there. He typically will contribute if he had any hard structures to him. But you generally have two different types. You have macroscopic or microscopic. So macroscopic generally is made up of shells, bones, and teeth that we could see with our naked eye. We don't need a microscope in order to see this type of biogenic sediment. So those shark's teeth that you like to collect, put on necklaces, that would be considered a macroscopic biogenic sediment because it came from biology. Whereas microscopic are like those shells that I showed you in the last slide. They create oozes, and typically it's the shells or tests of the plankton or microscopic organism that is creating this type of biogenic sediment. All right, so microscopic, you have two main types. You have the ones that are made out of silica, and you have the ones that are made out of calcium carbonate. The silica-based ones are from organisms like diatoms and radiolarians. And your calcium carbonate ones are made from coccolithophores and foramiferas. Your silica-based biogenic sediment are created by these two guys right here. The image on the left-hand side in the middle is an image of a diatom. It's a little hard to see, but it's on its side right now, but essentially it looks like a petri dish that has two halves that come together. And these diatoms are algae, so they do photosynthesize. And their shells, when they fall down to the bottom of the ocean, create a biogenic ooze that contributes to diatomaceous earth. So if any of you guys have pests at your home, like ants or roaches, this is a really good pest control that will kill ants and roaches. You'll see it at hardware stores all the time. But essentially it's just made out of these guys, the shells of these guys. Then you have radiolarians, which is the image on the right hand side there. Radiolarians are protozoans, which just means that they need to hunt for their food. They need to eat. They cannot photosynthesize. And they make really interesting structures. They typically will have a lot of spines and appendages on their shells. So again, siliceous, any sort of ooze needs to be greater than 30% by volume. It needs to be shells and not rocks. So on the right hand side there, you can see a better image of a diatom. You can see the two plates coming together. And then on the left-hand side there, you can see those are all radiolarians. They create all sorts of different shell shapes. They have, some of them look like UFOs. Some of them look like spiky balls, like little urchins. That one that has 3 appendages on it kind of looks like a dog toy. And then next you have calcareous ooze. These are created by organisms that use calcium carbonate to create their shells. So on the image right there, that is a foraminifera shell right there. So it's not as pretty as a radiolarian, but it still functions. It still looks like a shell. So in here, again, has to be 30% by volume, more than 30%. And these 4 guys right here contribute to calcareous oozes. You have your coccolithophores, which are just little balls of organisms that surround themselves with these round plates. Right, so each one of these plates is a calcium carbonate plate, And when these guys die, all of those plates will fall into the deep ocean. Then you have your foraminiferas that create these nice calcium carbonate shells. And then you have your pteropods. Your pteropods are deep ocean creatures. They do create a calcium carbonate shell that is internal. And those guys are pretty cool. Alright, so coccolithophores are responsible for this image on the right hand side here. Does anybody know what that image is of? If you said that this image was the White Cliffs of Dover in England, then you are correct. Coccolithophores, the plates from coccolithophores, are responsible for the reason why these cliffs are white. They are considered nanoplankton, which means not even a microscope can see them. You would have to use a scanning electron microscope, which just means that you have to get really, really fine detailed zoom in order to see these guys, because that's how tiny they are. They are photosynthesis. They do photosynthesis, and their plates at one point in time fell into this area, created a very large sediment of these plates, and over time and sea level rise and fall, these cliffs came up above the water, and now they are white. They did lithify, which just means that they turned into rock. So that ooze, that loosely consolidated pile of shells and plates from this guy, eventually over time with a lot of pressure and probably a little bit of heat, turned into a rock. And then now this cliffside right here is, when you look at it, it's comprised of these shells. All right, so generally you'll find biogenic ooze in the deep ocean. So they are pelagic deposits. You don't generally see them in the neritic region. And factors that determine whether you'll have biogenic ooze or not is mainly productivity, whether you have a lot of plankton or organisms at the surface. Depending on how deep those plates or shells descend to in the water column, they could be destroyed. And so we'll talk, I don't know if we talked about the compensation depth, but we should talk about it. And at a certain point, the ocean becomes slightly acidic to the point where calcium carbonate no longer exists and readily dissolves into solution. Or you have dilution, meaning that it is mixed together with other types of sediment, like lithogenic sediment. And if you don't have greater than 30%, then it's not considered an ooze. All right, so let's look at this graphically here. You need to have high productivity. So if you're in an area where you have a lot of organisms at the surface, like this image suggests, then you will create an ooze at the bottom of the ocean. But if you are off to the side, off to the left-hand side of that pile there, you won't get a lot of accumulation, or you won't get enough accumulation of these shells to create an ooze. You'll just create abyssal clay, right? So that's all that one is suggesting. So you have to have a lot of organisms at the surface in order to create this ooze. So here we go. So destruction, yeah. So there is a point in the ocean which is known as the calcite compensation depth, or the CCD. And this is where calcium carbonate readily dissolves back into solution. So it's not a shell that you can, or not a particle that you can see within the water, but it becomes dissolved, much like that sugar in that cup of coffee. Eventually that sugar dissolves into the coffee. Same thing with calcium carbonate. And depending on the rate at which the shells are falling will determine whether the shells dissolve or not. So if you have a lot of shells falling, typically that rate of dissolution of the calcium carbonate will be much slower because you have a lot of shells falling. Now, if you only had a few shells falling at a time, then the dissolution of the calcium carbonate would be able to keep up with the amount of shells falling into the deep ocean. Hopefully that made sense. Typically, warm, shallow ocean water is saturated with calcium carbonate, so you don't see a lot of dissolution near the surface of the ocean. But once you get into the deep ocean where it's cold and there's a high pressure and more acidity, that tends to be undersaturated with calcium carbonate. So that means that there's still room in the water molecules to dissolve calcium carbonate. So if you put calcium carbonate in the deep ocean, it will dissolve. And there is an area known as the lysocline, which is a depth at which calcium carbonate starts to rapidly dissolve into the water. So let's look at an image here. You can see in this image here, it shows about 3 miles below the ocean surface where calcium carbonate is saturated. And so it's not going to dissolve. But once you get below the CCD, that's where you have colder temperatures, you have higher pressure, you have more CO2 dissolved into the water, which means that the water has a lower pH, so it's more acidic. And when you have more acidic water, calcium carbonate will tend to dissolve very quickly. So below that point, you don't see any calcium carbonate shells, whereas above the CCD, you see the white speckling. Well, that's what's known as white snow. So if you were to go into the ocean at, like, say, about 1 or 2 kilometers, you'll see it looks like it's snowing in the ocean because you'll see a ton of white particles. But once you get below that point, then you won't see that anymore because all of that calcium carbonate is dissolving. Now, as you approach the CCD, that's where the lysocline is at. All right, so below 5,000 meters in the ocean, calcium carbonate is scarce, and you typically will not find calcium carbonate unless it has a cap over it, which we'll talk about later. You'll see some previous calcareous oozes in the deep ocean because it has a cap over it, and I'll show you an image of that in the next slide here. But oozes that are deposited above the CCD and then make their way forward or deeper into the ocean need to have that covering, otherwise it will be dissolved. So on this next slide here, I show you an image of what I'm talking about. So in the middle of that image there, you have a mid-ocean ridge, and it is spreading away from the mid-ocean ridge. So any of that calcium carbonate ooze that is falling on top of the ridge is just fine because it's above the CCD. But then at a certain point, if it continues to move off of the ridge and into the deep ocean, if it has not been covered by either abyssal clay or siliceous ooze, which you see on either the left or the right hand side in the brown and green colors, if it has not been covered by that, then it will dissolve. The blue area, the calcium carbonate ooze, will dissolve once it gets below the CCD. But we do see previous calcareous oozes that have been covered with abyssal clay or siliceous ooze, and then you can see that previously it did come from an area that was above the CCD. Okay, so that was biogenic ooze. So let's talk about hydrogenic sediment now. Hydrogenic sediment is particles that have gone into, that have been dissolved into the water, but now have come out, have precipitated out of the water. So for instance, when that calcium carbonate is dissolved in the deep ocean, if that calcium carbonate comes up to the surface, it will precipitate out and become a solid calcium carbonate again. So these types of precipitation generally occur when you have changes in temperature, pressure, or when you have some sort of chemical acting with the fluid or with the water itself. So let's look at some different types. So we have manganese nodules, we have phosphates, carbonates, metal sulfides, and evaporative salts. So let's look at each one right here. So manganese nodules are very interesting because they look much like the image on the right hand side there. They look like little lumps of minerals, basically. They look like rocks, but they're not. They're made up of manganese, iron, and a bunch of other minerals like cobalt. A lot of rare earth minerals are in manganese nodules, and they accumulate really slowly, and typically you'll see a seed in the middle of them that starts them off, and then they will grow outward from that seed. But they are very slow in accumulating and growing. And a lot of these minerals are rare earth minerals that are found within these nodules here, and they can be used in electronics. So for instance, cobalt, if you guys are looking at this on your laptop or computer or your cell phone, there is cobalt within your device right there. So these manganese nodules were discovered on the Challenger expedition back in the late 1800s, and typically you'll see about 16 million tons of these nodules accumulating each year, but they grow so slowly that it takes them anywhere from it takes them a million years to grow anywhere from 1 to 10 millimeters in diameter. So that's not a lot of growing that happens, but essentially it happens because they are precipitating out the minerals from the water into that solid rock structure. Mining of these nodules hasn't really taken off. As you can see in the image in the middle there, these are back in the day people mining for manganese nodules. But even though mining for collecting them from the bottom of the ocean isn't the issue here, the issue is that technically speaking, it's really expensive and really hard to extract those minerals from the nodules. You also don't have high market value for these metals because a lot of these metals that you find within these rocks can still be mined from land at a cheaper cost. And additionally, who owns these manganese nodules? They occur in the middle of the ocean where nobody really owns the material there. So, who has the right to these minerals? And then lastly, typically you'll see them around hydrothermal vents. So if we go mining for these, how will the biological communities around the vents, what would be the effect on those communities? Essentially, there's a lot of unknowns to this type of industry. Phosphates are another type of hydrogenic sediment, and that's just where you have a lot of phosphorus near the surface of the ocean that typically is generated by biological productivity. Phosphates will then precipitate out and generally is used in fertilizer. carbonates, so that calcium carbonate that we were talking about, you have two different types. You have aragonite and calcite. Calcite is typically what you'll find in a coral reef, but you do find some aragonite. That's just different types of calcium carbonate. But they create oolites, which are just small little round balls of calcium carbonate. And these oolites have been used in pharmaceuticals, so medicines and like toothpaste and stuff like that, as well as in construction. So who here lives in a house with drywall? If you do, you probably have oolites within your house there, because that drywall is made out of calcium carbonate, or what's also known as dolomite. All right, and then you have metal sulfides. So you can get iron, nickel, copper, zinc, silver, and other minerals or metals around hydrothermal vents. And these metals tend to precipitate out of the water cloud that comes out of the vent. Once it extends away from the vent and it starts to rapidly cool down, then those metals will precipitate out of the water. And lastly, you have evaporites. So these are minerals that forms when seawater evaporates. So a really good example of this is table salt or gypsum. Gypsum's another form of calcium carbonate that precipitates out and is also used in drywall. You definitely need high evaporation rates for this particular sediment to occur, and either you need to have a restriction from the open ocean. Well, you need to have restriction from the open ocean, and you need to have high evaporation rates. So here's just an image of salt being produced in the Death Valley. And so you can see all of that white material is salt that has evaporated. Now let's talk about cosmogenic sediments. These are sediments that are brought in that are extraterrestrial, and you have two different types. You have your microscopic and you have your macroscopic. So we're all familiar with the macroscopic, which is the top image there. Meteorites of varying sizes can create some pretty significant craters. And then microscopic are these tektites down in the bottom right hand corner there. You can see they are small rock-like materials that come from space. And typically they form an insignificant proportion of the ocean sediment, but you do see them in the ocean. On a yearly basis, we get about 300,000 metric tons of space dust each year on the Earth's surface. So why do we study the sediments? One good example is in biogenic sediment, you can see different isotopes. So oxygen-16, which is the most abundant type of oxygen on Earth, generally occurs when you are in warmer temperature waters, whereas oxygen-18 generally occurs when you have colder temperatures. So you'll see a higher abundance of oxygen-18 in colder waters. And let's just say those plankton down in the bottom right-hand image there, if you see that the concentration of oxygen-18 is higher in those shells, then you know that those shells were produced up in colder waters. Whereas if you see a higher concentration of oxygen-16, then those are from warmer waters. So in a sense, you can kind of get a sense of where these sediments come from just by looking at the chemistry. All right, so now here's just an overview of the different sediment types and where they come from. So you can see the continental shelf area. You have your lithogenic sediment. You can also have in that lagoon there, you can have hydrogenic sediment, those evaporative salts. You can get biogenous from the coral. You can get microscopic space debris. You can get windblown dust into the open ocean from land. You can get turbidites in those turbidity currents. You can get abyssal clays, your manganese nodules. You can get your siliceous and calcareous oozes, depending on where you are. So keep this image in mind now. Alright, so here's just a graphical image of all the different types of marine sediment around the world. And what I want you guys to focus on are the two main sediment types that are most abundant within the ocean. So what I want you to see is that abyssal clay and calcareous ooze are the two types of marine sediment that are most abundant in the ocean. You can see that lithogenic sediment generally occurs around the coastlines of the continent. You have a little bit of siliceous ooze that's yellow. You'll have a little bit of diatom related siliceous ooze around the polar regions. And then you have some other types, which are probably manganese nodules and such. But you can see majority of the open ocean sediment is abyssal clay or calcareous ooze. Alright, now let's look at thickness, because depending on where you are in relation to a mid-ocean ridge will determine whether you have a lot of sediment or not a whole lot. Now in the Atlantic there, you can see the middle part of the Atlantic has very thin sediment, and that's because the mid-ocean ridge is right there, and it's creating new crust, and so that new crust hasn't had a lot of time to accumulate sediment on it. Whereas on the edges along the coastline of Africa, South America, and North America in the Atlantic Ocean, you can see the sediment starts to thicken, and that's because it's not only getting sediment from the continent, but it's also much older, so it's had time to accumulate sediment. Whereas if you look at the Pacific Ocean, you don't see a lot of sediment accumulation in the Pacific because you have a lot of subduction zones within the Pacific that's destroying a lot of that sediment accumulation. Over in India, you can see the Indus fan that's creating quite a lot of sediment accumulation because a lot of that sediment is being run off by the Indus River. Now, energy resources that you can get from sediments are petroleum, gas hydrates, sand and gravel, salts, phosphorite, manganese nodules and crust, and rare earth minerals. So you can get all of these from the sediment. Petroleum, so we can get petroleum. They are created by microscopic organisms that decompose under pressure and heat. So petroleum is created when you have a lot of heat and a lot of pressure compressing all of that microscopic biogenic sediment. And as it's decomposing, it's creating basically oil and gas. A lot of the oil that is produced in the ocean is in the continental margin, and more than 30% of the oil that is produced or that we use on land comes from the ocean. A lot of times you will see oil spills and effects to marine ecosystems from these oil rigs that are in the ocean. Next, you'll have gas hydrates. These clathrates form under high pressure and low temperature, and under those circumstances, you'll get a very ice-like solid. But once these hydrates, like methane hydrate, starts to warm up, become loses that pressure and gets exposed to oxygen, they will decompose quickly and actually will self-ignite when exposed to oxygen. So you can see that image on the left-hand side there. That is methane hydrate that was just left out on the countertop and is now burning because it is exposed to oxygen. It is at low pressure and it is at a warmer temperature. So in the ocean, you can see a lot of methane hydrates down in the deep ocean. So in terms of climate change, this would be very drastic if these methane hydrates were to either warm up in temperature and lose some of its pressure that's in the deep ocean. And they will release a lot of methane into the atmosphere if they are allowed to ignite or decompose. Next, you can get sand and gravel. So a lot of times, beaches like Waikiki Beach here in Hawaii, they typically will, bring in new sand to replenish the beach that disappears in the wintertime. And so to do that, they typically will dredge out sand from the deep, from the continental margin or from other places around Hawaii. So Waikiki Beach typically will get its sand from Maui. But you can also find deposits of valuable minerals and gemstones in sand as well too. But it's typically not actively mined for at the moment. Next, you can get your table salts, so your evaporative salts. These are minerals that have precipitated out of solution. So you get your halite, which is just table salt. You get your salt deposits, like the ones in the Mediterranean Sea, or you can get calcium carbonate evaporites like gypsum, so the stuff that's in your drywall. Next, we have phosphorite. Typically, these are found in nodules, much like the manganese nodules. They generally occur in shallow depths, less than 300 meters, and they are on the continental shelf. They are not currently mined for, but if they were mined for, they could be used for fertilizer. And lastly, we have rare earth minerals. There are 17 metallic elements that are known as rare earth because they are harder to find here on Earth. But typically those minerals are used for electronics, so your cobalt in your laptops and electronic devices. They are used in optical machines. They are also used in magnetic and catalytic applications. Your fluorescent light bulbs has lithium in it, as well as batteries. And then around Hawaii, we found about 2,500 or 25,000 metric tons of rare earth minerals. So that is ours. We get to do what we want with it because it is within our jurisdiction. All right, so that was it for Chapter 4. We will be talking about Chapter 5, seawater chemistry, next.